Good morning, students. Now, I want to explain about the chemical equilibrium. నేను ఈరోజు మీకు కెమికల్ ఈక్విలిబ్రియం టాపిక్ గురించి ఎక్స్ప్లెయిన్ చేస్తాను. కెమికల్ ఈక్విలిబ్రియం what is chemical equilibrium? Means generally we know rate of forward reaction is equal to rate of backward reaction in that is called as a chemical equilibrium. Generally we call it, but in chemical equilibrium I will explain easily, you can understand. You take any బాక్స్, ఇక్కడ ఒక బాక్స్ తీసుకొని మనం లెఫ్ట్ సైడ్ నుంచి యూ అప్లైడ్ ద ఫోర్స్, రైట్ సైడ్ నుంచి కూడా మనం ఫోర్స్ అప్లై చేసినట్లయితే ఈ బాక్స్ అనేది ఎక్కడికి కూడా మూవ్ కాదు. ఇట్ ఈస్ ఫిక్స్డ్ ఎట్ దట్ పాయింట్, అక్కడనే ఫిక్స్ అయి ఉంటుంది. మీన్స్ ఈక్వల్ ఫోర్సెస్ అప్లై చేస్తే దిస్ ఈజ్ కాల్డ్, దీన్ని ఏమంటామంటే మనము స్టాటిక్, అంటే స్టాటిక్ ఈక్విలిబ్రియం. దీన్ని మనం స్టాటిక్ ఈక్విలిబ్రియం అంటాం. నెక్స్ట్ ఒక బీకర్ తీసుకొని దాంట్లో ఒక ట్యాప్ ద్వారా వాటర్ వేసినట్టయితే దీనిలో వాటర్ లెవెల్ ఒక మెయింటైన్ చేసి దీంట్లో వాటర్ పోసినట్టయితే నెక్స్ట్ ఎంత అమౌంట్ అయితే మనకు ఇక్కడ వాటర్ వస్తుందో అంత అమౌంట్ ఆఫ్ వాటర్ ఇటు సైడ్ నుంచి కింది నుంచి రిమూవ్ చేసినట్టయితే ఈ వాటర్ లెవెల్ అనేది సేమ్ మెయింటైన్ చేస్తుంది. ఎంత అమౌంట్ ఆఫ్ వాటర్ అయితే అవుతుందో అంతే అమౌంట్ ఆఫ్ వాటర్ రిమూవ్ అవుతుంది. ఈ ఈ వాటర్ లెవెల్ మెయింటైన్స్ సేమ్. దీన్ని ఏమని చెప్తామంటే మనము, బట్ ఇదైతే ఫ్రెష్ వాటర్ విల్ కమ్, పాత వాటర్ ఏదైతుంది మూవ్ అవుతుంది, బట్ దిస్ ఈజ్ ఆల్వేస్ మెయింటైన్ సేమ్ లెవెల్. ఈ ఈక్విలిబ్రియం ఏమంటామంటే డైనమిక్ ఈక్విలిబ్రియం అంటాం. ఎందుకు డైనమిక్ అంటే మూమెంట్లో ఉంటుంది కాబట్టి దీన్ని మనం డైనమిక్ ఈక్విలిబ్రియం అంటాం. దీన్నేమో స్టాటిక్లో ఉంటున్నాడు. స్టాటిక్ మోస్ట్ ఆఫ్ ద కెమికల్ రియాక్షన్స్, మన కెమికల్ ఆల్ ఇన్ కెమిస్ట్రీ ఆల్ రియాక్షన్స్ ఆర్ this follows the dynamic nature. These all chemical equations are chemical equilibrium are dynamic in nature లో ఉంటాయి. డైనమిక్ ఇన్ నేచర్ అన్నీ కూడా నాట్ స్టాటిక్. ఆల్ chemical reactions, first remember, are in equilibrium with dynamic in nature. These points we have to remember. In chemistry we know different types of reactions. First there are two types of reactions. One is irreversible reactions, next we know reversible reactions. We know. What are the irreversible reactions? Acid base reactions. Acid combine with base, they will form salt plus water. Irreversible reactions means only one direction, only forward reaction will happen, it will not backward reactions. Reversible means two types. These are equilibrium. hydrogen reacts with iodine, they will form equilibrium with 2HI, like this. Acid base reactions, acid you take HCl, if you take any base, strong base, sodium hydroxide, they will form the salt NaCl plus water. This is only one direction. That's why this is irreversible reaction అని చెప్తాం. ఫార్వర్డ్ అండ్ బ్యాక్వర్డ్ రియాక్షన్ రెండు అయినట్టయితే దీన్ని రివర్సిబుల్ రియాక్షన్ అని చెప్తాం. నెక్స్ట్ సెకండ్ వన్ ఈస్ if you form any decomposition reactions, combustion reactions, you take carbon combustion with oxygen, they will form carbon dioxide. This is a only one direction reaction, combustion reaction. This is a combustion reaction, this is a irreversible reaction. Next precipitation reactions, we take precipitation reaction. What is precipitation reaction? If you take silver nitrate react with HCl, they will form silver chloride plus HNO3, whatever it may be. If you take silver hydroxide water, this is silver chloride is precipitate. After precipitate, it is separated from the reaction. That's why this is not comes backward. This is a irreversible reaction. This is not undergo backward reaction. Combustion reactions, acid base salt formation reactions, these three are irreversible reactions. Many reactions are there in chemistry, but these three will show irreversible reactions. If you take reversible reaction, we can write many things. Nitrogen oxide combined with oxygen, they will form nitrogen dioxide. If you otherwise nitrogen plus oxygen, they will form nitrogen dioxide, whatever it may be. If you write here NO2, 2NO2, you write 2NO2. If you write a Haber process ammonia formation, N2 plus 3 hydrogen gives rise to 2 ammonia. If you react with sulfur dioxide plus oxygen, they will form sulfur trioxide. This is a Haber process. This process is called Haber process. This is preparation of sulfur trioxide is a contact process. These are some of the examples of reversible, irreversible and reversible reactions. Next, after that, we discuss about the reversible reactions. Next, here we want to discuss about the reversible reactions. Reversible reactions not discussed in the chemical equilibrium. Chemical equilibrium explain about the only equilibrium process. That's why we will discuss about the reversible reactions. For example, if you write A plus B gives rise to C plus D. A plus B, if you form C plus D, this is known as a forward reactions. Forward reactions. దీన్ని మనం rate of reaction ఎట్లా రాస్తామంటే rate of forward reaction is directly proportional to concentration of A into concentration of B. If you write C plus D gives rise to A plus B, this is the backward reaction. This is దీన్ని మనం backward reaction అని చెప్తాం. Backward reaction. దీని rate of reaction ఎలా రాస్తుంటే rate of backward reaction is directly proportional to concentration of C into concentration of B. This you write like this. Next, you equate them, means rate when it is obtained equilibrium, the rate of forward reaction is equal to rate of backward reaction. Then only it will apply in the equilibrium. We know this. rate of forward reaction is equal to rate of backward reaction, then only it will obtain the equilibrium. Write it. Rate of forward reaction A concentration of B is equal to rate of backward reaction if you put by removing this, you can write as a rate of forward reaction is equal to rate of backward reaction. Rate of forward reaction is equal to, right, rate of forward reaction is equal to, this is taken as RF, rate of backward reaction is equal to, this is taken as a constant, this is RB. Rate of forward reaction is equal to rate of backward reaction, we know. Rate of forward reaction is equal to rate of backward reaction, then only. That is RF into concentration of A into concentration of B is equal to RB into concentration of C into concentration of D. We know this. Then RF by RB, this comes here. Then this is cross multiplication. Concentration of C into concentration of D by concentration of A into concentration of B. This is taken as a K equilibrium. Then K equilibrium is equal to concentration of C into concentration of D by concentration of A into concentration of B. This is the K equilibrium expression if rate of forward reaction is equal to rate of backward reaction. This we have to remember, very very important. This is the equilibrium expression. Next we write, initially what will happen? A plus B consumes, they will form C plus D. This is the rate of forward reaction. Next, C plus D, after reaching equilibrium, they again increases the concentration. Then again C plus D concentration decreases. Then again they will form the A plus B. This is the backward reaction. This is the forward reaction. This is the backward reaction. That is rate of forward at equilibrium. Rate of forward reaction is equal to rate of backward reaction, because this is a dynamic in nature. Equilibrium is, we know, I will explain, dynamic in nature. That is rate of forward reaction is equal to rate of backward reaction. This is the expression for K equilibrium. Next, write the graph expression. Well, how to denote with the graph? If you take graphs for rate of reaction, this is for rate of reaction versus with the time t. How to represent? This is rate of reaction with the time. First you have to start with the forward reaction, they will like this. Then forward reaction concentration decreases. This is rate of forward reaction. With the time decreases, time increases, rate of reactance is concentration decreases, we know. If time passes, the formation of products is increases, rate of formation, at once they will combine, they will form this one. This is the equilibrium point. This is the equilibrium point at time t. The rate of forward reaction is equal to, this is the rate of backward reaction, rate of the reaction. This is, you must remember, only one graph exists for rate of reaction. This is the graph. But in case of concentration, we take, this is in case of rate of reaction, rate versus time. The equilibrium graph, only one graph existed. But you take in case of concentration versus time, there are three graphs are existed. Here you take, this is the one graph, this is concentration versus time. We know the reactants product is the equilibrium point. Next, this is the rate of forward, this is the reactants, this is the products graph. Next, concentration versus time. We know this is the after reaching the concentration remains constant. This is the reactants products graph, and also the, if you take, this is the equilibrium point. This is also one more graph, concentration versus time. These are the reactants and this is the products. Here also this is the reactants, this is the products. For concentration versus time, there are three graphs are existed. For rate of reaction is this one. Here rate of forward reaction is, rate of backward reaction is. Here combined they will, this is the equilibrium point. But in terms of concentration, this is the equilibrium point. After reaching they remains constant. But this is also equilibrium point. The reactants and concentration is, after reaching equilibrium they will remains constant. Here also this is the equilibrium point. After reaching equilibrium the concentrations will remains constant. This is about the four graphs. This is rate versus time and this is the concentration versus time. You must remember. Next, characteristics of chemical equilibrium. Now I want to explain about the characteristics of chemical equilibrium. This is very, very important. Characteristics of chemical equilibrium. Characteristics of chemical equilibrium. What are the characteristics of chemical equilibrium? First, I will explain. This is dynamic in nature. Dynamic in nature. First introduction I will explain. Dynamic in nature. Next, equilibrium can be achieved from either direction, either from forward reaction side or backward reaction side. We can achieve the equilibrium. Next, third point, what is happen? Catalyst, role of catalyst. Role of catalyst. What is the role of catalyst? Catalyst, it will enhance the reaching of the equilibrium as early as possible. Means it shows the how quickly equilibrium is achieved. If you take for example, it initiate the reaction to reach the equilibrium as quickly as possible. For example, if you write this one graph, we know this is the equilibrium point with the time rate of reaction. If this is no catalyst, this is if you use the catalyst, the equilibrium reaches as early as possible. This is the in presence of catalyst. By using this graph you can understand easily. In presence of catalyst, catalyst helps the reaction to as early as possible to approach the equilibrium. One more important is the equilibrium must be closed vessel. In closed vessel only, then only it will obtain the equilibrium. Otherwise, what will happen if it now you use the closed vessel? The gases, if you not closed vessel, they easily escape from the reaction solution or reaction side. Uh, why? Because this is after if escape, they for backward reaction it cannot happen. That's why they must be in closed vessel only. They will possible. These are the some of the characteristics of chemical equilibrium must have to remember. Next. Next, we read the law of mass action. What is law of mass action? How the equation is presented? Law of mass action. This is explained by Guldberg and Weig scientist. These two scientists are derived the law of mass action. If you take for example A plus 2B are equilibrium with 3C plus D. This is the chemical reaction. This is the for these are initially this taken as a this is concentration of A means these are the active masses. Active masses. It is not made concentration. These are the active masses. Active mass of A, active mass of B, active mass of C, active masses. Active masses means the amount which participated in the reaction. Participate reaction. If you take the concentration of A, in this 100% is not participated. The amount, the part which participated in the reaction, that is called as a active mass. This you know. This you have to remember. For this, we write the rate of forward reaction is equal to RF into active mass of A into active mass of B square. We know. We write like this. Next, you know, rate of backward reaction is equal to RB into active masses of C and active masses of D. At equilibrium, we know rate of forward reaction is equal to rate of backward reaction. Means that is RF into active mass of A into active mass of B square is equal to RB into active mass of C into active mass of D. We know. Means next RF by RB is equal to active mass of C to the power of 3 by active mass of D by active mass of A into active mass of B square. This we know. Next we write this is equal to K equilibrium. This is K equilibrium. This is the derivation for this reaction. For example, if you take this is law of mass action is derived from this Guldberg and Weig scientist. This is the representation for this chemical reaction. Very, very important how to represent the equation. We know there are two types of equilibrium constants that exist. There are two types of equilibrium constants. There are two types of equilibrium constants that existed in this chemical equilibrium. One is Kc, one is Kp. These are the two equilibrium constants that exist in this chemical equilibrium. One is Kc and another one is Kp. Kp. Kc means this is taken as a N by V concentration. This is active mass. Active mass will be presented by this concentration. This is taken as in molarity. Number of moles per volume means in case of concentration Kc, this is taken as a molarity. For these cases, this is active mass is considered as a pressure of the gas. Active mass. This is taken as a gaseous system. We know this is taken as a gaseous system. Active masses is taken as a gaseous system. We know how to write PV is equal to nRT. We know from this graph. Pressure is equal to N by V into RT. Means pressure is directly proportional to N by V, means molarity. This is RT. This is for Kp in case of Kp. In case of, this is active mass of in case of Kc. What is the relation between Kp and Kc? This you have to remember, very, very, very important. After that, we will derive this. After this, we can derive the relation. That is Kp is equal to Kc into R to the power of delta Ng. This you have to remember, very, very, very important. Next, we derive this equation. What is the relation between Kp and Kc? How to derive? Next, we derive the equation Kp relation with Kc. Kp and Kc relation. For example, if you take, this is the equation. What is the relation? Kp is equal to Kc into R to the power of delta Ng for gaseous system. The units for this one Kp is in atmosphere. We know this is Kc is moles per liter, or we know constant. We take 0.0821 liter atmosphere. Temperature is Kelvin. Delta Ng is means products minus reactant. Gaseous system. Delta Ng is equal to, in the reaction, the product coefficient minus reactant coefficient. The difference between product minus. This is the each one, how to represent, what is the significance of each one, and also what are the units for this equation. Next, we have to derive the Kp-Kc relation. First, you take, for example, A plus B gives rise to C plus D. I have to take this one. How to write the equation for Kc? We know Kc in case of number of moles, that is concentration of C into concentration of D by concentration of A into concentration of B. This is the for Kp, K equilibrium Kc. We know what is the result. Kp is equal to, we know. Next, pressure of C, partial pressure of D by partial pressure of A into partial pressure of B. We know from this equation PV is equal to nRT. We know P is equal to N by V into RT. P is equal to, this is the concentration, number of moles, for example X, whatever it will be, RT. Means pressure is directly proportional to this one. We substitute here. Pc means concentration of C into RT. PD means concentration of D into RT. For example, if you take this one is 2B and 3C, we take this one. Means this is B square C to the power of 3. Next, B square and C to the power of 3. Write like this. This is easily you can C to the power of 3 into R to the power of 3. We know. Next, concentration of A into RT into PB square, means concentration of B square into, this is RT whole square. This we know. This is equal to, how to write? Concentration of C cube into D by concentration of A into concentration of B square. Concentration of B square. This is RT 3 plus 1. R to the power of 3 plus 1. 4 minus 2 plus 1, 3. Means 1 only. This is the real equation for, we know, Kc. Already we wrote there. This is Kc into R to the power of 4 minus 3, 1. This is the Kp. This is the equation for Kp into Kc is equal to R to the power of delta Ng. Means if you take, this is the difference between delta Ng is equal to 4 minus 3, this is equal to 1. If you take n times like that, this is the taken as a delta Ng, this is equal to 1 in case of this one. This is the relation between Kp and Kc relation. This is very, very important, must have to remember. What are the units for this each unit in this Kp Kc relations, and also how the relation will comes derive the equation. This is very, very important, you have to remember. Next, I will explain about the I will explain the chemical equilibrium. What are the characteristics of equilibrium constants? Before I will explain chemical equilibrium characteristics, now I want to explain characteristic of equilibrium constant. Equilibrium constant. How equilibrium constant is depends or does not depends. For example, if you take this is, first we have to write 2. It does not. If you take it does not depends upon, it does not depends upon, that is K equilibrium constant. It does not depends upon initial concentration. It does not depends upon the initial concentration, and also it does not depends upon the catalyst. So which catalyst you have to use, that is does not depends upon the K equilibrium. And also third one is it does not depends upon the addition of inert gases. Addition of inert gases. It does not depends upon initial concentration and catalyst, and also does not depends upon the addition of inert gases. And these are the some of the 3 examples which in on what factor it will depends. Very, very important. It depends upon first one is temperature. Very, very important. This is equilibrium constant depends upon temperature. Very, very important. This is must have to remember. And also the representation of reaction. Representation of reaction. How to represent the chemical reaction, that is depends upon the chemical equilibrium reaction, but does not depends upon these factors, some of the factors, but it only depends upon temperature and mode of representation of reaction. Very, 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 very important. These 2 we will discuss next. First, I will explain the mode of representation of reaction. First, I will explain the mode of representation of reaction. Mode of representation of reaction. Mode of representation of reaction. This is very, very important. Must ask in the question. First, take one reaction. A plus B gives rise to equilibrium with C plus D. This is K equilibrium. Next, C plus D equilibrium with A plus B. What is the equilibrium constant? This how the reaction is represented? They reversed. A plus B from C plus D, but C plus D here equilibrium with A plus B. Means if reverse the reaction, then K equilibrium is equal to K dash. Take K dash is equal to 1 by K equilibrium. This is very divided with this one. This is very important. K dash is equal to K1 by K equilibrium. If you first case we write K equilibrium is equal to conservation of C into conservation of D by conservation of A into conservation of B. In second case K dash is equal to write it conservation of A conservation of B by conservation of C into conservation of D. If you reverse this one, what will happen? The first case will be 1 by K dash. If you write this way 1 by K equilibrium, what will happen? This is A into conservation of B by conservation of C into conservation of D. This is the equation. If you take, for example, A gives rise equilibrium with B. If this is K equilibrium, if this is multiplied with 2A with 2B, what will happen? K dash. If it is multiplied, K dash is equal to K equilibrium square. If multiplied with this one, then we will get the K equilibrium. If divided with 2, what will happen? K equilibrium is equal to K to the power of 1 by 2. K dash is equal to, it will obtain root. If reverse the reaction, this is reciprocal. If multiply with, then you get the square. If divided with by 2, then we get the K1 by 2. If adding two equations, A gives rise to equilibrium with B, B equilibrium with C. What is the A equilibrium with C? This is K1, this is K2, this is asked. What will happen? Here K equilibrium is equal to multiply K1 into K2. If these two equilibriums are added, their equilibrium constant must be multiplied, because addition of these two they get cancelled, then K equilibrium is called K1 into K2. If A equilibrium with B, C equilibrium with A, this is K1, this is K2, then K equilibrium is equal to, if minus, what will happen? K divided with K2 division. This is the fifth one. These are the representation of the chemical equilibrium. How to must remember, they will ask question in definitely one of the question in the mains. A plus B gives us to C. If reverse the reaction, there is 1 by K equilibrium. If multiply with any factor, then we will get the square. If division with this one, we will get the root. If add those two equilibriums, I have to multiply their equilibrium coefficients, constants. If divided with, if minus, they will get division, K1 by K2. This is the representation of the chemical equilibriums. You have to must remember, very important. Next depend factor, that is temperature. How it will react depends upon the temperature. This is next we have to discuss. Very next, this is very important factor. The temperature depends upon temperature. We know Arrhenius equation. This is log K2 by K1 is equal to delta H by 2.303 R into 1 by T1 minus 1 by T2. This is the very important equation. Must remember, this is very important reaction. How it is depends upon, first you take delta H is equal to 0, there is no heat exchange of reaction. What will happen? Log K2 by K1 is equal to 0, means here K1 is equal to K2, K2 is equal to K1, this no depends. If you take for example second case, if delta H is equal to negative, what will happen? Means this will get negative. Log K2 by K1 is less than 0, negative means this factor is less than 0, means K2 is less than K1. Means if temperature is negative, what will happen? If temperature is decreases, lower temperature, we know exothermic reactions are lower temperature is favorable. If temperature is lower, this is forward reaction is happen. Lower temperature is favorable. If you take delta H is positive, what will happen? Log K2 by K1 is greater than 0, means K2 is greater than K1. What will happen? Temperature increases, then K2 reaction is favorable. This is the endothermic, higher temperature is favorable, that is K2 by greater than K1. If delta H is negative, means this is favor for lower temperatures, means less than 0. Means if temperature increases, for example, if temperature increases, means the rate of reaction is decreases. K1 is lower, but temperature increases, this is favor. If temperature increases, here low temperature. That's why this is lower temperature. Temperature decreases, K2 reaction will favor. What is the graph for this reaction? We have to write these two graphs. If you take this, for this graph, log K versus temperature, log K versus temperature for endothermic reaction. Endothermic means this, exothermic that one. If temperature increases, what will happen? The rate of log K to what will happen? Increases. Temperature increases, this is increases from here to, this is the graph for this one. If you take for example exothermic reaction, what will happen? Log K versus temperature, log K versus temperature, what will happen? If temperature increases, low temperature are favorable, but if temperature increases, what will happen? From here to exothermic reaction, this is decreases. Temperature increases, K1 is, if temperature increases, K1 is, log K will be decreases. This is the graph for exothermic reaction. These are the two graphs, very very important. They will ask in the questions. Endothermic reactions means higher temperature favorable, exothermic means lower temperature is favorable. This is about the mode of representation and also the temperature depends. This is very very important. Next, after that, based on this, get the problems. Then next, this is about the chemical equilibrium, but on this except problems, this is chemical equilibrium. Next topic we discuss after problems. We explain about the ionic equilibrium. Thank you students. Thank you very much.